Hello everyone, thank you for coming. My name is Guilherme and today I'm going to talk about structural parameterizations for equitable coloring. This work was done while I was a postdoc at Universidade Federal de Minas Gerais under Professor Vinicius, and it's also joint work with Matheus Guedes, which was one of our undergrad students. Okay, so first things first, we're going to talk about a lot in this next 20 minutes about equitable coloring. And what is equitable coloring? Well, it's just a coloring of the vertices, a k-coloring of the vertices of a graph, such that the size of two color classes differ by at most one. Okay, so an example, I'm going to give you a claw, and you're going to say, okay, it is two-colorable in the traditional sense. You just put a red in the middle vertex, blue in the outside vertices, but then you realize, okay, this is not equitable. It's definitely not equitable because red is used once, blue thrice. So we need a third color to make this really simple bipartite graph, to get an equitable coloring of this very simple bipartite graph. Okay, so why are we interested in this problem? Well, it's got a bunch of applications. Some are known for a lot of time, for over 20 years, such as the application in processor task scheduling, which was shown in Baker and Kaufman to be a viable model for their problem, their target problem. It's also been known to be useful when dealing with communication control and server load balancing, among other applications, which I'm not going to list here because it's a lot of applications. Okay, so as any graph problem, especially coloring problems, we've got some parameters associated with this object, this coloring, this property of graphs. And the first one of them is the equitable chromatic number. So if we say that a graph has equitable chromatic number k, we're saying that k is the smallest integer for which we can find a k equitable coloring of our graph. So very, very simple, and we've got a big conjecture which has been open for a long time, which is just Brooks' theorem. So, but for equitable coloring, it says that the equitable chromatic number is at most the maximum degree of the graph, except for complete graphs and not wholes. But we've also got another interesting parameter, which is the equitable chromatic threshold. We say that a graph G has equitable chromatic threshold k if for every integer at least k, we have an equitable chromatic coloring of G. So we have a very nice theorem, which is the Heinold-Zabrati theorem, which says that, okay, any graph is equitably k-colorable if you give me at least maximum degree plus 1 colors. But getting to the Brooks bound of delta is still not known to be true. We have evidences for some classes, which are listed in this very nice survey of Lee, but this survey just says structural properties, classes for which this property holds. It says, okay, in this class, this conjecture is true. In this class, this conjecture is true. But the general cases, it's not known so far. Okay, so we're going to talk about complexity, and it's a nice way to start with classical complexity. So we have classes, we have the respective complexity of the problem. So for trees, forests, co-bipartite graphs, the problem becomes polynomial. It's also polynomial in co-interval and split. But for pretty much everything else you check, it's going to be NP complete, even for a fixed number of colors, such as bipartite graphs. And one thing we notice is that there's a nice generalization of split graphs, which are unipolar graphs, for which the complexity of equitable coloring was not known. And what we did was going to show, okay, we can do a bit better than split graphs. We can solve the problem in polynomial time on unipolar graphs. Okay, so let's talk a bit about unipolar graphs. A graph G is unipolar if and only if it has a clique Q, such that G minus Q is a disjoint union of cliques. In this example, V1 and V2 form the central clique, while V3, V4 are one of the disjoint cliques, and V5 and V6 are the other one. But how do we solve this problem, our problem on this graph class? Well, We begin by guessing a coloring of the central click, and this coloring is unique. We can just color it with red and blue, for instance. And then we begin to build a flow network to run max flow on and get the solution. We have a bunch of vertices, and the first set of vertices represent the colors that we use on the central click. The second layer of vertices represent a pair color click, and they exist so we can control that in each click only one vertex gets a color CI. For instance, we can have V3 and V4 with a color green, for instance. And finally, on the last layer of vertices, we have the vertices of G minus Q itself. So V3, V4, V5, and V6 in our example. And how do we create the arcs? Well, we begin with a color. So we have we pick an arc from S to a color CI, say S to C1. And then, well, we're going to use C1 now. And which click are you going to use? We can use click 1 or click 2. If we choose click 1, which vertices can be colored with C1? Well, in our example, it's only V4 because it's not adjacent to the red circle in the central click. And then V4 is colored, and we're done with this vertex. And we repeat the process until we're done. And that's it. That's what max flow gives us. The best way to assign colors to the vertices of G minus Q. No mystery, that's it. The proof is very direct, and we're not going to talk about it right now because there's no point to do that. Okay, so let's talk about parameterized complexity. Just a quick primer. A problem is NP hard if there's no exact algorithm that solves all instances in time polynomial on the size of the input. So now we're going to give up on solving all instances and focus on instances that have a chosen parameter to be very, very small. So a size of k is going to be much smaller than the size of the instance itself. And this is very, very useful. It solves a bunch of problems. It gives us a nice way to analyze problems much richer than the classical P versus NP questions. And we have more or less 3 classifications of problems in this theoretical framework. The first is the efficiently solvable problem, the FPT problems, which we can solve in f of k for some computable function k times a polynomial on the size of the instance. And the best example is vertex cover, parameterized by the size of the solution. But not everything is good news. There are some problems where we just cannot find these algorithms unless some really strange things happen in complexity landscape. And there are some W1 hard problems, as they are known, that cannot be solved in the f of k times n to a constant. And the best example is click, parameterized by the size of the solution. And there are even problems which are para-NP hard. That is, even if the parameter is a constant, we cannot solve them in FPT time, nor any other time. They just cannot be solved very efficiently. And the best example is vertex coloring, parameterized by the number of colors. Okay, so what parameterizations of equitable coloring are known, have their complexity known? So obviously the number of colors, which is natural parameter, is going to be para-NP hard. But we have some positive cases like vertex cover and max leaf number, which yield FPT algorithms. But a bunch of other parameters turn out to yield W1 hard parameterizations like tree width and tree depth. And what we did in this work was settle 3 lines of this table. Specifically, we solve cluster and co-cluster plus KV graphs, and we show that disjoint path plus KV is W1 hard. Okay, so what is a cluster graph? Recall the definition of unipolar graphs. We just had a bunch of disjoint clicks and a central click. A cluster graph is just the second part, just the disjoint clicks. This graph is obviously not a cluster graph because it has a connected component which is not a clique. But if we remove this set of 4 vertices, which we call the modulator, we have a clique, a cluster graph. So let's remove it. Ta-da! Each connecting component is a clique. And we say that G is a cluster plus KV graph if there is a set U of size at most K that makes G minus U into a cluster graph. And how do we solve this? Well, it's just the algorithm for unipolar graphs, but now the coloring of the central piece of the modulator is not unique. We may have K to the K possible colorings. And that's what we do. For each possible coloring, we construct the flow network we described before, the exact same flow network. Because it solves the problem of deciding whether or not a given coloring of the modulator can be extended to the satellite cliques, the clusters themselves. And that's it. We just have to be a bit careful with the capacities of the SC arcs, but that's really simple. It's as you think it should be. It's not going to be very hard. Finally, for disjoint paths plus KV vertices, we're going to show that it's doubly hard by an intermediate reduction from multicolored clique, parameterized by the number of ports, to list equitable coloring by the number of colors plus the size of the modulator. And how do we do this? Well, we interpret a multicolored clique as a collection of k-squared edges between the parts of the input graph. And so each edge of the input to multicolored clique is going to become two vertex disjoint gadgets. And we need to enforce 3 properties. The first, selection. So between each 2 parts, we must pick only one edge to be in the solution. So this is going to give us, to do this, we're going to need O of k squared colors. We need to enforce symmetry. That is, if I choose a color, if I choose this edge from I to j, I must choose the same edge from j to I. Again, you need k-colored colors for that. Q-colored colors. And finally, we need consistency. So if I have an edge from Vi to Vj and an edge from Vi to Vl, I must enforce that the same endpoint, they have the same endpoint in I. And to do that, we're going to need a cubic number of colors. Okay, so our gadgets, they are just paths. There's nothing magical about them. The magical part is on the lists and how we divide this gadget. So to divide it, we're going to choose the 3 properties: selection, symmetry, and consistency. So each one of these pieces is going to fulfill one of those 3 roles. And the idea to construct the lists is that a coloring of the selection piece of the gadget propagates the entire gadget. So it could be a gray coloring, a gray blue coloring that says, okay, I'm not going to pick the corresponding edge in the solution, or it could be a blue-red coloring which says, okay, I picked this edge in the solution. And then the propagation happens due to the numerical targets that we ensure are well formed, and because of a trick that was first shown by Fellows and friends in their proof that equitable coloring is W1 hard parameterized by 3-width. Alright, so it's been a long time since we submitted this paper to Latin, and then we were able to get a bunch of new results, thankfully. Chief among them are a cubic kernel for max leaf number, and the proof that no polynomial kernel exists when parameterizing by vertex cover and number of colors. This yields us 3 main open problems. First, can we find a subcubic kernel when parameterizing by max leaf number? We do not know how to do this. Our technique does not appear to work. Second, can we prove using ETH or Seth that the currently known algorithms have optimal running time? That is, can we beat the 2 to the k log k running time we currently have in these problems? And finally, the crown jewel of these problems is, can equitable coloring be solved in FPT time when parameterized by feedback edge set? This is more or less how the parameterized landscape works. We have the polykernels for max leaf, distance to click over here, the polynomial, the FPT algorithms for vertex cover, distance to cluster over here, and a bunch of hard cases, and the three main open problems, which is feedback vertex set plus max degree, feedback edge set, and distance to threshold. Thank you very much, and I will answer your questions if you have any.
Guilherme, for your talk. And please, are there comments or questions?
Yeah, hi, I have a question. Guilherme,
Hello.
You showed the reduction to list equitable coloring in order to show that it was W1 hard, right?
Yeah.
Is there an equivalence between list equitable coloring to the actual equitable coloring problem on disjoint K paths, or disjoint paths plus KV? Because list equitable coloring generalizes the equitable coloring problem, right?
Yeah. Actually, what we did, it's an intermediate reduction, because what we showed for list equitable coloring is that it's W1 hard when parameterized by number of colors on disjoint paths. We don't have the plus KV. And to get to equitable coloring, you actually need to encode the lists, right?
Yeah.
And we do that with a click of size K.
Oh, okay. So the result comes from.
Yeah.
So, okay, so on the table you showed that it was W1 just for disjoint paths, and then the encoding of the list comes from the KV. Okay.
Yeah, exactly. Yeah.
Awesome. All right, thank you.
Thank you.
I have a quick question.
Yeah.
You showed a table showing results of NP completeness in the beginning. And I noticed that for interval graphs, it's NP complete.
Yeah, that's right.
Correct? I didn't find proper interval graphs in the table.
Oh, yeah.
Are there results for proper interval graphs?
Yeah, it's solvable in polynomial time.
Polynomial time. Okay,
yeah.
as expected.
Yeah, we have a paper in ICGT 2018, which was published in the MTCS in 2019, that shows that cloth-free chordal graphs are solvable in polynomial time.
Okay.
Thank you, Jaime.
Thank you. More questions or comments? Okay, let's thank to the speaker.